So in our group, we make and use quantum dots, which are cadmium selenide nanoparticles. So today I'm going to start out by showing you how we make them. In here we have some stearic acid and cadmium oxide that we heat up to dissolve the cadmium oxide in the stearic acid. And then we cooled it back down and added some trioctylphosphine oxide and some hexadecylamine. And then we heated that up again until it all melted. And we have been putting it under a vacuum to get rid of all of the water inside. The first step, if you can see, there's some accumulation of the cadmium oxide and stearic acid on the wall. So I just need to heat that up to melt it off so it falls back down. So I'm just going to use a handy blowtorch. And you can see as I'm heating this up, it's falling back in. I don't want to heat it up too much, so try to go slowly. So now that that's ready, I'm going to go and head over to make the selenium for the injection. So this is a glove box. It's filled with argon, and it serves two purposes. The first is to protect us from the chemicals. Some of them give off bad odors that could be harmful to the body, so we keep them in the glove box. And the second is to prevent the chemicals from degrading in the presence of air. So I'm getting two things in here. The first is selenium, which is in powder form, and then I'm going to dissolve that in tributylphosphine. And then I'm going to take that, split it between two syringes, and head back over to do the injection. So first I'm just measuring the selenium powder, but the selenium is the component that we add in excess. So now I'm just going to dissolve it in the TBP. And when I dissolve it, it is an exothermic reaction, so it heats up a little, but not to an unbearable amount. It takes a little bit of mechanical stimulation to get this to dissolve, so I just shake it up. So now I'm going to split this between two syringes so that we can inject it faster, and so that everything is injected more at the same time, and therefore it will grow to be about the same size. So now that these are ready, I'm going to get them ready to be taken out. Okay, so now we've been vacuuming for about 2 hours, and we've gotten rid of all of the excess water in our reaction flask. So I'm going to go ahead and put it under argon again, the same as was in the glove box. So I'm putting it under argon in order to prevent reaction with the air. And I just do that by flipping this switch right here. So now it's off of vacuum, and it's on argon. So now I can turn off the vacuum pump. And I can set the temperature now to 300 degrees and wait for it to heat up. So now I am injecting the selenium, and you can see the color changes immediately. I'm going to lower the temperature to 290 degrees to anneal it. You can see in the beginning it fluoresces green, but as it heats up it turns to a more red color. So now we just wait about 12 minutes while this anneals. So after this process is over, we have what we call the quantum dot cores. And this is essentially the quantum dot, but it's imperfect. The shell, or the exterior of the quantum dot, is not very smooth. And those imperfections mean that it doesn't glow as bright as it potentially can. So we do another process where we put a shell around that to help smooth those imperfections and get very bright quantum dots. And after that whole process is complete, we end up with the finished product. And these we can tailor to be different colors, but these are in chloroform or hexane. They're in an organic solvent, and if we want to ever use them with things in the body, we need to put them in water. In order to put them into water, we end up usually with a much more dilute solution, and we cover them with lipids, which basically are two components. They coat the quantum dot with the hydrophobic portion, and then the exterior of the lipid is hydrophilic or water-loving. And you end up with something like this. The reason they fluoresce is because they're excited with the UV light. So when we take away that UV light, they no longer glow. At this point, the quantum dots have annealed, and so now we are able to just cool them down to a temperature where we can clean them. And as they cool, they get brighter. So at this point, the reaction is over. So if I excite them with the black light, you can see that now they fluoresce. At the lower temperatures, we're able to see the color much more clearly. Quantum dots are very versatile in their applications. Anything that could be identified or detected with a glowing marker could be identified or detected with a quantum dot. For example, cancer cells are what we identify in this lab. So often cancer cells have markers on their membrane, on their external membrane, and we're able to use that to target those markers with our quantum dots. And then we're able to distinguish cancerous cells from non-cancerous cells in the lab. Once we have our quantum dots in water, we can activate them with antibodies, which are what we use to target the cancerous cells. And then we incubate the quantum dots with the cell lines and various different cell lines to see whether or not the quantum dots will adhere to the cells. And so here, when that's all finished, we look at them with the microscope. And we just put it on the microscope, and then we are able to view the cells in a variety of different manners, both with the phase contrast, which is what you see normally with your eye, and also with different fluorescence. Right now we're looking at images of the cells, cancer cells, that have been targeted by quantum dots. And this fluorescence, or glowing, is the quantum dots attached to the cell membrane. The video is looking at different focal planes, so it focuses on the bottom of the cell and then up to the top of the cell. And you can see that the glowing is the brightest around the perimeter of the cell where the quantum dots are adhered. I am Charlie Dvorak, a member in Dr. Searson's lab at Johns Hopkins University.